Welcome to Physical Science 101, Physical Science Survey. This is a two-semester series. This is the first semester. And this is the first of 14 lectures, one for each chapter in this course. And the format for each lecture will be similar to this one. I will call up some PowerPoints in just a minute, and we'll work off of the PowerPoints. But if a concept needs further discussion and explaining, that's why I have this whiteboard back here, so I can make some points or work some problems, whatever the case may be. All right, so let's get started. And I need to share the PowerPoints for this chapter. There. And there we go. All right, so I'm going to turn this into a slideshow, if it will let me. There we go. Okay, and I make some adjustments on my side. You can't see what's going on here, but I'm moving some things around so that I can see things a little better, a little clearer. Organize my desktop. The first thing you'll notice is that the cover of the physical science, an introduction to physical science, the textbook, is a different cover than the one you'll be getting, either hard copy if you want, or since you are buying Cengage Unlimited to get access to the textbook and to the homework, then you will have the textbook in electronic form. And it will look more like this. That's the 14th edition. This is an earlier edition. I believe it's maybe even the 13th edition. But the material is essentially the same. All right, first topic, first chapter is on measurement. And in fact, the first 3 chapters are essentially classical physics, often called Newtonian physics. And it'll become obvious by the time we get through chapter 3 what I mean by Newtonian physics. But for now, we need a discussion of science, scientific method, and the way that we use measurement to gain information about a particular problem. Okay, here we go. So I'm going to open my hard copy so I can follow along here and see what's coming. First, before we talk about measurement, we need to get a clear understanding of what we mean by science. In the popular literature and in the news media and popular culture, science is a term that's thrown around as if everybody knows what it is. And for the popular culture and for the mainstream media, science means whatever they want it to mean. So they have an agenda, and they use science to justify their preconceived notions. Science, in fact, is actually derived from a Greek word that means truth or knowledge. And that's rarely the case for the science that's espoused in the mainstream media. But in this course, we're going to use that definition. So, and there's been over the decades, in fact centuries, there have been methods developed for obtaining this knowledge in a form that other scientists can appreciate and can understand, and hopefully will maintain the integrity of each of the scientists, because if the work that is published by a scientist is unreliable, then you need a way to figure that out. You need a way to know it. So we're going to talk about that as in the next few slides. Okay, so science is a broad term that basically means what is the character of nature? Can we describe nature? Can we describe what's happening in nature? Can we predict what will happen in natural settings if we know the starting conditions? Those are all valid questions for the scientist. And in order to do that, we need some way to measure the world. Now, sometimes we measure by what we consider length, width, height, mass, various descriptive terms that are also have also attached with them numbers that describe those measurements. Sometimes our measurements are what we would call qualitative. That is, there are no numbers associated with them, such as what color is it? Or did it make a loud sound? Or compare two things. Is this one lighter than that one? Okay, those are all also valid observations and in some respects measurements of the physical world. But if we are going to make measurements, we need a way to guarantee their accuracy. In other words, is the measurement that we obtain, and usually when we say measurement, we're thinking in terms of quantitative, that is, numbers. Are those numbers that we obtain for that measurement accurate? Can we rely on them? And we're going to discuss how to do that also. Okay, for this course, we're discussing physical science. And physical science, for our purposes, excuse me, is a subset of the natural sciences. There are various types of natural sciences. One of them might be biological. In other words, the sciences that study living systems. The physical sciences are agreed upon to encompass physics, chemistry, geology, in other words, studying the earth, meteorology or weather, and astronomy, that is everything outside the earth. For Physical Science 101, we're going to be looking at physics and astronomy only. The second semester course will cover chemistry, geology, and meteorology. All right. And this is another way of looking at the subdivisions of the sciences. And this, I believe, comes, and most of these slides come straight out of your textbook. I supplement them occasionally with material that I think is valuable, instructive, and helps explain a concept. But most of the slides are based upon your textbook, so they should look familiar. So if we take the sciences, we have social sciences and natural sciences are completely different animals. And then within the natural sciences, that is nature, study of nature. We want to have knowledge, understanding of nature. Those can be physical sciences or biological sciences. So if there are living systems, we're talking about biology. If they're non-living systems of any kind, we're talking about the physical sciences. And then, of course, these subdivisions that we discussed earlier. And sometimes in some courses, there will be a combination of both of all the three, astronomy, meteorology, geology, as earth and space science. Earth science, of course, by itself would just be geology and meteorology. And then we attach astronomy to this last category. Okay, so let's move on. What constitutes a scientific investigation? Well, we have to know how we're going to make measurements. We're going to know how we're going to describe the physical phenomenon. And in order to do that, we need a basis for the research. Before we can even make a measurement, we have to understand how we're going to approach the problem beforehand. And that usually begins with observation. In other words, you see or hear or taste, use your senses to observe something about the physical world. And then you ask questions. In other words, if I observe a blue sky, maybe I want to know why that sky is blue. Because if you look at the sun, of course, you don't want to do that with a naked eye. You want to use some sort of protection. But looking at the sun or looking at a picture of the sun, you see that the sun is almost white with a slight yellow tinge. So if the source of the light that illuminates the sky is white or nearly white, then why is it blue? That's a valid question. We want to know why that is. So we need a method for making measurements, observations, to try to understand, try to answer that question. And in order to do that, there is one major assumption that has to be made. We have to assume that the universe, that is, everything we see, everything we hear, taste, our world, is orderly and can be understood. If we don't believe that in the beginning, then what's the point? Because you may make an observation or a measurement 1 second, and 2 seconds later make the same observation and get different results. And that's no way to gain information, understanding about our universe. It has to be orderly. So what we've come up with is what's commonly known as the scientific method. Now, the scientific method is not a fixed step-by-step procedure. It's more a framework. So depending on what science and what question you're trying to answer, the scientific method may be modified to accomplish your goal. But there are certain general categories and steps that you proceed through in the scientific method to obtain answers. And one way of thinking of the scientific method is it is actually a subcategory of critical thinking. In other words, critical thinking is taking apart what you observe in the world and understanding its parts, resynthesizing them to gain an understanding. Another way of looking at it is also a skeptical mind. Just because somebody tells you something doesn't necessarily mean it's true. In other words, and I'm going to be telling you lots of stuff in this course. So what you need is a supporting message from other sources. The textbook, websites perhaps, and you have to be careful there because just because it's on the internet doesn't mean it's true. So you need a discerning mind. Primary sources are the best. In other words, a primary source would be a published research paper on a topic. And those are good examples, good samples of primary information, because in order to publish in a referee journal, you have referees. You have other scientists scrutinizing your work and criticizing it before it even goes to print. Okay, so that's also part of the scientific method. Anyway, so we can break the scientific method down into first observation. In other words, you notice something that sparks a question. And once you have that question in mind, then you consider, you may have to make more observations before you finally consider a possible answer to the question. And you may have several answers. You may have, but you have to pick one before you can test to see if that answer is correct, or it's even close to being correct. And that's commonly referred to as a hypothesis. It's an explanation for the observed phenomenon. And then that hypothesis is subjected to experiment. In other words, if the hypothesis, the statement, answers the question, then you should be able to recreate a situation with known parameters at the beginning. And if your hypothesis is correct, then you should get the answer that you have observed before. Now, you can recreate the system, and the experiment confirms it. Now, once you've, it usually takes several, sometimes hundreds of experiments in order for you to gain a knowledge, and each time you may change things about your hypothesis and re-experiment. But eventually, you are able to, let's see, I think I have a slide on this. Yeah, I better continue with this slide. Once you've conducted your experiments and gained confirmations of your hypotheses, then very often you're able to devise a law, what we call a law. A law of nature simply says that if the conditions are A at the beginning, then you will always get B at the end. In other words, it just says A yields B every time. Or if you change A, say A plus 7, then B will be plus something, and that's your answer. The law, one thing a law does not do is say why you go from A to B every time you conduct that experiment. That is reserved for theory. Theory tries to explain why the law happens the way it does. So generally speaking, laws come first, then followed by theory. Okay. So let's say we're going to make measurements during an experiment. And over the decades, scientists have managed to develop sophisticated methods and equipment, procedures for making very accurate measurements of physical phenomenon. These may be the distance something has movement, or temperature change. What is the temperature now? What is it after the experiment? We even have accurate measurements for weather. As strange as that may seem, our meteorologists are getting better and better and better at forecasting weather conditions further into the future. Now, the future might be 2 or 3 days, but that's, believe it or not, that's much better than it used to be. We measure time. There are a whole host of different measurements for which we have established standards and methods so that all scientists can agree that when a measurement is made and reported, everybody understands what that means. That's very important. If the community doesn't understand what you're saying, then you might as well be talking a foreign language. Nobody understands what you're saying. They have to be agreed upon values for these measurements. And there are numerous examples of measurements that are reported in our textbook and examples that are used with these measurements to work problems. We call them problems, but the problems result from the outcome of experiment. So the textbook has been vetted by experts and it gives you reliable information. So the textbook actually presents primary sources in its references. Now, there's also the issue of uncertainty. Can we measure with certainty every phenomenon? And the answer to that is a simple one word: no. With every measurement, there is uncertainty. The source of that uncertainty can be almost anything. We might be able to identify the source of the uncertainty. Maybe you've got a meter stick that you observe is smudged here and there, so you can't really see the numbers accurately. Or if it's a metallic one, maybe it's been bent. Any number of things can explain inaccurate measurements. The uncertainty that gives us problems are those uncertainties that cannot be identified. Those are called random errors. The first type, where you know the cause of the error, the potential error, those are systematic errors. And those are fairly easily identified and compensated for in measurement. But the random errors are not. So that's where statistics is used. How do we treat measurements in our experiments so that we can gain a reliable value, or we know the range within which our measurements are reliable? So the takeaway from that discussion is every measurement has some uncertainty associated with it. And in fact, the smaller and smaller the measurement gets, the more difficult it is to get an accurate measurement. Because what we've discovered over the decades is that the smaller the physical phenomenon or object that is being measured, the more influence the observer has on that measurement. In other words, if you try to measure the length of a car, you can be fairly certain that measurement through 10 different times, and you get fairly close measurements each time. But if you try to measure an atom, where it is, how fast it's going maybe, or the size of the atom, the smaller the object, the simple act of measuring will change it. So it becomes more difficult to get accurate measurements of very small objects. All right, so those are the potential problems that arise when you're trying to make a measurement, and we have to account for those. And anyone reading our research, if we publish it, will have to be informed how we dealt with those potential uncertainties. Otherwise, when you read a research paper, which I've read many of them, either as a consumer of the information or as a reviewer, the first thing I look for is, after I understand the problem, That's explained at the very beginning of the article. Then I look at the methods, and I see what method did this scientist use to answer the question that has been explained in the introduction. And if I find that the method is no good, then I'll critique it if I'm a reviewer and send it back to the publisher and say, this needs to be explained better. But if I'm a consumer and it's already been published and I find that the method is not valid, I throw it in the garbage. It's no good. I don't waste my time on the results because the method is garbage. Okay. I mentioned quantitative data earlier. Quantitative means you get a number. And you don't just get a number, actually. You get a number and a unit of measure. We'll talk about that a little more later. And here we have qualitative data. The difference between quantitative and qualitative is quantitative usually has a number, actually always has a number, and qualitative data is more a descriptive term, which will describe perhaps some general physical property or some change that has occurred. It's an observation, a valid measurement, but it's not a quantitative measurement. All right. So here's what I mentioned earlier, the hypothesis. The hypothesis is a possible explanation for the observations. And you can just, once you've made an observation and you think you know what has happened, how to explain it, then you formulate that into a statement which can be tested. So, for example, matter consists of small particles, atoms, that simply rearrange themselves. That would be a hypothesis. Then you have to say, all right, if that's true, how do I test it? How do I test that matter is made of small particles? Well, do I have an instrument that can look into a substance and see the atoms? Yeah, we do now. We can, in some cases, actually see the atoms. But if this were 100 years ago or 150 years ago, no, you couldn't. You need to come up with some other way to prove that matter consists of small particles. Okay, so that's a possible hypothesis. Maybe it's just an educated guess, right? An educated guess sometimes is better than an observation based upon your experience. Right? If you've been in this line of work, if you've been investigating for years and years, sometimes your educated guesses are pretty good, but they still need to be tested. So you devise an experiment to test whether that hypothesis is true. And that hypothesis will be considered valid only if it predicts results. If you conduct the experiment and the hypothesis predicts the results of the experiment, then you have support for your hypothesis. I hesitate to say confirmation because confirmation implies that you have an absolute answer. And absolute answers in sciences they just don't exist. In other words, when you hear in the mainstream media or popular culture lost my train of thought. I was looking for the right word. If you hear anyone say such and such is settled science, then you know right there and then that they're lying, or they at least don't know what they're talking about. There's no such thing as settled science. Science is always changing. That's the nature of the beast. Science changes. So when someone says global warming is settled science by consensus of the majority of scientists, you know that they're lying. It does not happen. Now, global warming is one possible explanation for the phenomenon that we see in nature, but it's not the only explanation. And it's open to change as more evidence is accumulated. We do experiments. So I'll leave it at that for now. And that's what this note says at the bottom. The hypothesis is never proven. In other words, you can't say that my experiment proves the hypothesis. What you actually are doing is you fail to disprove the hypothesis. In other words, the only thing that can be proven is that your hypothesis is false. But if you fail to disprove it, that is support for your hypothesis and may require more experimentation, and usually does. That's often called job security. In other words, when you conduct an experiment, you usually come out of the experiment with a dozen or more new questions that need answering. Okay, so I'll leave that for now. The ideal experiment is a test of your hypothesis under controlled conditions. In other words, you try to control all the parameters and make sure that they don't change during the experiment. And the only thing that changes is the one that you're investigating. Then any observation that you make of a change can be attributed to the one parameter that you allow to change. Sometimes that's not possible. And there are statistical ways to tease the information out. But the ideal experiment is one in which all variables are controlled except one. Then that makes it easy to associate outcomes with the initial experimental conditions. The other thing that you need to be certain of is that anyone else who picks up your research and duplicates your experiment will arrive at the same results. That is essential. If your experiments cannot be duplicated, then they will not be supported by other scientists. That happened several years ago with two scientists, I believe they were at the University of Colorado, who claimed that they had produced fusion at room temperature in the laboratory. Okay, remember, fusion is the holy grail of energy production. Right now, the only type of nuclear energy we have is fission. We take atoms, usually uranium-235, and split it. And when it splits, it gives off energy. All right, lots of it. Well, the other way is to fuse atoms together. That happens at the center of the sun and all stars, as a matter of fact. And when that happens, you get lots of energy. Well, they claimed that at room temperature, they had produced cold fusion. And they published it. Some journal was crazy enough to believe them. And then other scientists tried to duplicate their work. Couldn't be done. Some smart scientists devised experiments that would take their work and use more refined techniques of measurement with the goal of finding out where they made their mistakes. And they did. They found out where their mistakes were made. And the short version is that those scientists are no longer employed by any university. In other words, it was a career-killing claim that they had made. So you've got to convince other researchers by making your research duplicatable. In other words, you've got to be able to publish your work in such a way that others can reproduce it. Now, when we talk about a concept or a model of nature, in other words, a model is like a, well, I like to think of airplane models that I've made as a kid. I had this small model that looked like a big airplane. Now, I understood that that model was not that airplane. It just represented that airplane in a small form that I could look at and maybe even make some changes to it. That's what a model is. And a model is always associated with a theory, because the model and the theory together explain how that system works. And if you understand how it works and why things happen the way they do, then you can change things about the model and make predictions about how that system will change with those. If you input the same starting conditions, but you change the model, then you should get a different outcome, and the outcome is predictable. So that's what we mean by predictions. When you have this model, then the predictions must agree with experimental results. Okay. Now here we have the law that I mentioned earlier. A scientific law is an explanation of what happens. It doesn't say why it happens. In other words, if you set the initial conditions, then the results are always the same. That is a law. For instance, the law of conservation of mass. And that's probably not a good example for this course, because we're not going to talk about chemistry. But this law says that during a chemical reaction, the amount of mass at the beginning is the same amount of mass at the end of the reaction. There's no gain or loss. Okay. So that's what a theory is. It's an explanation for why something happens. An example of that is the atomic theory. And the atomic theory has held up for over 200 years. It was proposed by John Dalton, and we'll cover that in the second semester. But this is a valid theory that is fairly solid, because it's been tested over and over and over and over again, and it's held up over 200 plus years. Now, what do we do if we propose a theory and somewhere down the line, an experiment produces results that do not agree with the theory? Right? That happens. It happens a lot. So what do you do with it? What do you do with your theory if the experiment doesn't agree with it? Well, you have three possibilities, right? You can restrict the theory's application. In other words, you can say, this theory works only under this narrowly defined set of circumstances, right? Then you can go on using it. And we'll look at laws. Actually, you can use this. These choices are valid for laws as well as theories. So Newton's laws of motion that we'll discuss in chapter 3 are a good example. Newton's laws work as long as the masses of the objects are not too big and not too small, in the middle. Then you can use Newton's laws. What else can you do? Well, you can modify the theory. You can tweak your model so that the outcome more closely resembles experimental results. And that's done a lot. In fact, sometimes it's done in a valid fashion, And sometimes it's done in an invalid fashion. In other words, the scientist who wants his model to give the answer that he expects, and then he changes the model to give him his answer. You find those scattered all through this global climate change discussion. There are 20 or 30 different models that can be applied to global climate change, and all of them fail. So the modelers don't want their model to fail, so they change the model so that it gives the outcome that they want. In other words, if they're expecting over the next century for the global temperature, average global temperature, to increase by 4 or 5 degrees centigrade, then they will change the model to give them that result. Now, that's what's known as an invalid modification of a theory. But you could modify your theory so it more closely approaches the predicted outcome and then test it again. Last option, throw it out. It cannot be restricted in its use, cannot be modified. Throw it out, start over again. And that happens sometimes also. So those are your three choices. This is a general outline of what you might, the process you might go through in the scientific method, where you have observations, which yield measurements, usually. And then you devise a hypothesis, an explanation, and then you test that hypothesis with more measurements. And you see if it explains the observations. Over time, you develop a law that can be applied to these physical phenomena, and the law is valid for most of the observations. And then you modify it if you have to. And then after the law has been tested for quite some time, and you may actually put together several laws and devise a theory. And then you can also test the theory. But there's a circuitous process here. In other words, you develop an explanation and you test it. It comes close, but not exact. So you modify and you go back to the hypothesis, change your hypothesis a little bit, test it again. And you keep going in that circle until you're satisfied that the experiments are being predicted by the hypothesis. Then you can devise a law. Okay, that in a nutshell, well, in a long discussion actually, is the scientific method. Okay, in making these measurements, we use our senses. In other words, sight is central to scientific measurement. But sometimes we use hearing, we use our sense of hearing, maybe our sense of smell. Taste, not so much, because tasting something can be hazardous. Smelling something can be hazardous too. Or you can touch it. You notice perhaps that it's hot, or you can get close to it and feel warmth. But the sight and the hearing, sight and sound, provide most of the information that our brains gather from the environment. But these senses have their limits. In other words, hearing, for instance, if you want to measure a difference in pitch, pitch is associated with so many cycles per second of sound waves hitting your ears. And those are measured in hertz. Right? Hertz. Which is equal to cycles per second. The human ear is generally, some humans are better than others, but generally the range is 20 to 20,000 hertz. Okay? So if the frequency of the sound is higher than 20,000 hertz, then you won't hear it. That's like a dog whistle, right? If you blow a dog whistle, you can't hear it, but the dog can, because the dog's sense of hearing runs higher than that. Or if the frequency is less than 20 hertz or 20 cycles per second, you won't hear that either. If the intensity is strong enough, you may feel the vibration. But actually picking out the less than 20, I think some whales can pick it up. And actually it travels very long distances underwater. But this is our range for hearing. Sight, right? We can't see anything that is less than 400 or greater than 700 nanometers in wavelength. And I'm going to explain what these values mean later. But this is our range. Anything less than that is ultraviolet, right? We can't see that. Or greater than 700, and this is a rough range. Greater than 700 is infrared or higher. And we can't see that either. So we have instruments that can make those measurements. And they overcome our sensory limitations. Oops, sorry. They overcome our sensory limitations by using detectors that are sensitized to things that are outside the range of our senses. And sometimes they measure things that our senses would never measure. And so these instruments are not just able to observe outside our sensory limits, but they're also more accurate. In other words, they can subdivide the divisions between very close measurements and get very fine detail. The other problem is our senses can be deceived. Optical illusions are examples, right? Look at this figure and say, this line A, this blue line A, and this blue line B, are they equal in length? Actually, they are. If you take a ruler and put it up to your screen and measure the length of A and length of B, you'll find that exactly the same length. But the measuring device is not fooled. Your eyes are fooled. Okay? So sometimes what you think you see is not really what you see. Here's another example. Right? Are the horizontal lines parallel or do they slope? Right? Horizontal lines, these orange lines here. They look like they change directions, don't they? But they don't. They're exactly parallel. How about this one? This is a weird one. Right? If you look at just the ends of this thing, you say, okay, there are three pegs right there, but they're attached at their base, right? If you follow this down here like that, you go, wait a minute. Right? That's not where it should be. It should be up here. We're fooled. Or are they going to be stuck into these holes? Is it stuck on the other side or are they stuck on the foreside? You can't tell. And if you follow this line around, you find that if you go here, that's on this dimension. But if you go here, it's on the wrong dimension. Right? If you go here, it's on a different dimension. So an optical illusion fools your eyes, but measuring devices are not as easily fooled. Okay, So if we're going to make a measurement, we need to agree upon the standard for that measurement. Okay, and that standard always includes a magnitude or a number and a unit of measure. Right? So if we say 12 inches, right, we have an intuition of what 12 inches is, right? It's a foot, right? The foot's about that long, about that long. But we have to have an agreed upon standard. What is an inch? Right? So we have to have somewhere, we have to have an agreed upon inch that can be held as a comparison. So if I have a ruler that I want to mark off in inches, I need to go back to a standard and set it and mark it off in inches. So 1 inch is the unit. Now these agreed upon standards are known as fundamental quantities. These are fundamental units of measure. And 3 possibilities are length, like inches. In the metric system, it would be meters. Mass, right? In the metric system, that's kilograms. And time is seconds. Those are fundamental units. And there are some others, but the focus here is on the fundamental unit, and then every other unit of measure can be derived from those fundamental units. For example, when we study force and motion later, it requires each one of these measures of length, mass, and time in order to give us information about forces and motion. And all of those concepts can be explained with just those 3 measurements. Now, those fundamental units, sometimes they are standard units, and sometimes they are derived from the fundamentals. In other words, the fundamental could be a standard unit, or the standard unit could be a derived unit from the fundamental. But whatever the case may be, the standard unit is fixed and reproducible. Okay? We have 2 major systems. In the sciences, no matter where you are on the earth, we use the metric system. Okay? But for common measurements in the United States, which is the only country left doing this, common units that are used are in the English system. Sometimes it's called the imperial system or the British system. Miles for distance, inches for length, pounds for weight, seconds. Of course, we all agree on seconds. That's the same for all the systems. The metric system and the British system, the problem with the British system is these units, they're related in odd ways. They're not uniform in the same way that the metric system is. So when I say something is 6,000 meters long, I could also say it's 6 kilometers. A kilometer is 1,000 times as big as a meter. So I only need 6 of them to be the same length. These are exactly the same length, right? But with different units of measure. The key to the metric system is it's based upon the decimal system. In other words, every increment in the number is a factor of 10. So there's the ones, tens, hundreds, thousands. And we can take these thousands units and put them into that prefix, K for kilo. Okay, so that's the beauty of the metric system. It's decimal based. And we'll look at, hopefully, yeah, we're going to look at that in a little more detail coming up. Okay. Now, even though the United States has officially adopted the metric system, way back, 1893, we continue to use the British system in our everyday measurements. For instance, we don't buy liters of gas at the pump. We buy gallons. Everywhere else in the world, you buy liters. But even though we officially adopted the metric system, it's still only used in sciences. In fact, the weather predominantly uses the English system. In other words, the measurement of temperature in weather forecasting is in degrees Fahrenheit, which is typically agreed upon as a English system. Metric system uses centigrade or Celsius. They're synonymous with one another. Okay, so this is just a brief history of the metric system in the United States. And I'm not going to spend a lot of time on this because I'm already long-winded and I need to get through this lecture before you go to sleep. Okay. So, if the United States uses the English system for so many things, but it also uses the metric system, what could possibly go wrong? Well, we've been trying to go to Mars for several decades now, sending robotic spacecraft up there. Some of them orbit the planet, some of them just fly by, and some of them try to land. Right? There was one probe spacecraft that was sent to Mars, the Mars Climate Orbiter. By its name, of course, you may guess that it was supposed to go into an orbit around the planet and make measurements from space. Well, something went wrong. $125 million was just flushed down the toilet. Why? Because the manufacturer of the Mars Climate Orbiter used the English system in building the spacecraft. In other words, in the software as well. So all the instructions sent to the spacecraft needed to be converted to the English system, right? Well, NASA, the space agency that is responsible for the space probe, its launch and nursing it on its way to the planet and getting it into orbit, use the metric system. And in fact, NASA had subcontracted that job to the Jet Propulsion Laboratory in Pasadena, well, actually, yeah, Pasadena, California. And the manufacturers, Lockheed Martin in Denver, used the English system. Well, what happened? Well, they didn't make the conversion correctly. The engineers that were trying to insert this spacecraft into an orbit put in values in the metric system, and the spacecraft thought that it was receiving instructions in the English system. So its course correction was wrong, And the next thing you know, the spacecraft crashed into the surface of Mars. It just flew right into the planet. Okay, so that's a case study in, you better know what your system is and the units of measure that you're using. Okay. All right. So let's look at length. Length is the measurement of one-dimensional space in any direction. In other words, that line has a given length. One direction from here to here, right? What, by the way, what would be a zero-dimensional representation? A dot. It has no height, no width, no length. One dimension has length, and length only. Now, if we want to use length in a two-dimensional setting, we have a length this way, and we have a length this way, right? So now we have two dimensions, you know, length, height, or width, whichever the case may be. Three dimensions, we would represent it like this. Now we have a measurement this direction, we have a measurement this direction, and we have a measurement this direction. Three dimensions. That is three-dimensional space, or in this case, it would be like a solid or a space that's lined out in three dimensions. But each one of those dimensions can be described as length. And then we can use the length to calculate any of the others. Okay. So any actual space is three dimensions. In other words, I am three-dimensional. The metric standard is the meter, which is a little over a yard, right? And in inches, 1 meter equals 39.36 inches, right? So it's 3 1/3 inches longer than a yard is a meter. Now, originally, the meter was defined in terms of the distance between the equator and the North Pole along the prime meridian. Now, we haven't studied the prime meridian yet. We will in, let's see, chapter... Oops. Chapter 15. We'll talk about the prime meridian. But anyway, that distance between the equator and the North Pole subdivided into a 10 millionth of that distance was taken to be the meter, right? So once they settled upon the community, the scientific community settled upon that length, that standard length, then what they did was they took that length and created a bar that has a cross section like this. Looks like an I-beam. That's the cross section, and then it goes like that. Okay. And they made it out of platinum and iridium alloy, which is resistant to corrosion, because once you establish that length, you don't want it to change. And in fact, they went beyond that. They took that bar and put it in an inert environment, a double bell jar, so to speak, which was flushed with argon so that there's no corrosion that could take place. And that was the standard. And they kept it in a cave in France so that the temperature fluctuation would be very stable. And that was the standard. If you wanted to standardize a meter of any material, then you would have to go to that location and compare it and have the experts at that site certify that your meter was accurate. Okay. Just for observation and information, British standard unit is the foot. Originally, it was approximately the length of a foot, and they probably used the foot of the king as a standard. Okay, so there's your distance between the equator and the North Pole is 10 million meters. And there's a comparison of the meter and the yard. And there's a cross section of the bar. I didn't do it quite right, did I? Anyway, that's just for illustration purposes. Now we have a different way of determining a meter. Now, what's the advantage of using a different method? Well, the method that's used is actually so many wavelengths of a particular light produced by a laser, and you have an instrument that can measure that many wavelengths of that light. And it will tell you that at that place, you have that many wavelengths, that's a meter. The advantage is you can standardize that instrument, and then you can measure or reproduce a meter anywhere. You don't have to go to that cave in France. All right. Now, how did they do that? Well, it takes a pretty sophisticated piece of equipment, and that equipment was developed by this man, William Meggers, right there, at the National Institute of Standards and Testing in the United States. And from the looks of his clothes, that's probably maybe in the 30s, 1930s. He used what was known as an interferometer. Now, I'm not going to go into how an interferometer works, but it was successful, tested, and successfully duplicated the standard meter. Right, so now we have a way to do it anywhere we want. How about mass? The standard of mass in the metric system is the kilogram. Okay, now why would we put a prefix, right? We know there's the gram, right? Why would we say kilo, which means 1,000? So why would the standard unit be 1,000 grams? We already have a gram. Why not make the gram standard, right? Well, the gram was grandfathered in. It was known and accepted for centuries by alchemists primarily as a standard unit of measure for mass. So we're sort of stuck with it. But the gram is very small. So what would happen if you had a standard mass made out of this platinum iridium alloy that was like that, and for some reason it got corroded on the surface or maybe a tiny scratch? What type of error would that introduce? Percentage-wise, it would be massive. So we want a larger mass that if very slight corrosion occurs, it will not impact the mass significantly. So that's why the kilogram was chosen, because the percent error would be minimized. The reference for the kilogram is still a platinum iridium cylinder, which was maintained in that cave, in the same inert environment as the bar for the meter was. We haven't come up with a way for standardizing the kilogram in any other fashion but the standard mass. Okay, there it is in its bell jar. Actually, it's a double bell jar. Okay. Oh, excuse me. That's not the original. This is a standard kilogram that's maintained at the National Institutes of Standard and Testing in Washington, D.C. And compared to the one in Paris, it's just slightly less than. Okay? But we know what it is, and it's that number. Okay, this is not really important, except to say that the British standard unit for mass is the slug. It's rarely used. We often use the pound synonymously, but the pound is actually a force. So that's where things get kind of messed up. If you say the mass of this object is 20 pounds, that's really not accurate, because that's a force, and I'll explain the difference between those two in just a second. So if you have something that you think weighs a pound on the surface of the Earth, then you take it to the moon, it's going to actually exert a force on the surface of the moon 1/6 of what it did on the Earth. So if it can change like that, then it's not mass, right? Because mass doesn't change no matter where it is in the universe. Mass is a measure of quantity of substance. That just illustrates the potential for problems when we mix our terms. Okay, so if you weigh 300 pounds on Earth, you weigh 50 pounds on the moon, that's a measure of force. And we'll talk a little bit more about force later. The time measurement has been accepted for centuries as the second. Now we measure the second very accurately. Originally, it was this fraction, 86,400ths of a solar day. But now we've standardized it to the point with what's known as an atomic clock. And we use the vibrations of the cesium-133 atom. So, needless to say, we know the second to many, many decimal places very, very accurately. And that's important, especially for satellite communications. Okay. So let me carry on here. This is measurement of a second. I'm not going to labor that point any further. So the metric system is sometimes known as the MKS system, for meter, kilogram, second. And like I said before, the beauty of the metric system is that it's base 10. It's a decimal system. It's administered by this bureau in Paris, but the standards are set in terms of the International System of Units, SI units. So if you see a reference to SI units, that's what they're referring to. International System, which it's backwards because it's French. 7 base units, or 7 fundamental units, are defined by the International System, and from those, all the others can be derived. All right. So these are the 7 units. The meter we've talked about, the kilogram we've talked about, second we've talked about, the ampere, which is a measure of electrical current. We won't talk about in this. That'll come in the second semester. Temperature, Kelvin. I don't think we're going to, let's see, we might talk about that one. Not so much. We're going to use temperature primarily in chemistry. So we'll talk about that one more in the second semester. Also the mole, the amount of a substance, chemistry. So stay tuned for the second semester. And then this one, the candela, luminous intensity. We reference luminosity when we talk about, when we get to astronomy, like how luminous is the star, or how much light is reflected by a moon or a planet. But this is the standard of measurement, the candela. There are other derived units that are more commonly used, but this is the standard. Okay, so the convenience of base 10 is illustrated here by 1 kilometer equals 1,000 meters, right? It's just 10 to the third difference, whereas 1 mile equals 5,280 feet, right? And that's a statute mile, right? There are two different types of miles, right? There's the statute mile that we use on the ground, and there's the nautical mile that pilots and boat captains use. It's defined a different way, right? So there you could have confusion. The meter is 100 centimeters. The yard is 3 feet or 36 inches, right? See how confusing that can get? You have to memorize what these values are in order to make conversions from one to the other. 1 liter is 1,000 milliliters. Milli means 1,000th of. So 1,000th of a liter is a milliliter, which means the units are smaller, so it takes more of them. It takes 1,000 milliliters to make 1 liter. Okay, notice that going from one to the others, if the unit of measure changes from a large unit to a very small unit, then the number in front of it goes from small to large. We go large to small units, the number goes from small to large units. And that's always the case. 1 quart, 32 ounces or 2 pints. 1 gallon, 128 ounces or 4 quarts or 8 pints. Right, see how confusing the British system can get. So that's why we stick with a metric system. Now these prefixes also help us modify base units or fundamental units so that we understand what they mean. Mega means 1,000,000 times. So a megagram is 1,000,000 grams. A kilogram is 1,000 grams. A centigram is a 100th of a gram, and a milligram is 1,000th of a gram. Look in your textbook in Appendix 1, and you'll find a complete listing of these prefixes. You need to understand what they mean. In other words, memorize them. Okay, so here we have, let's see, I'm making some adjustments to my my screen here, sorry. So here we have a liter, which is a base unit for many of the measurements we make in the sciences, but it's not a fundamental unit. The liter is a derived unit from measurements of length, right? So it represents the volume of something, a gas or a liquid or even a solid. It represents the volume, but it's based upon measurements of length. So if we have a cube with 10 centimeters on one side, 10 centimeters on, say, length, width, height, that's 1,000 cubic centimeters, which is 1 liter. Okay, that's it. Now there are relationships that we can derive for masses and volumes. 1 liter of pure water has a mass of 1 kilogram or 1,000 grams. So 1 cubic centimeter of water has a mass of 1 gram, right? If 1,000 cubic centimeters is a liter, and a liter weighs 1,000 grams, then 1 cubic centimeter of water is a mass of 1 gram. So this cubic centimeter is also a milliliter, right? A milliliter is 1,000th of a liter, and it takes 1,000 milliliters to make a liter. So if it takes 1,000 cubic centimeters to make a liter and 1,000 milliliters to make a liter, then the obvious conclusion is the milliliter and the cubic centimeter are synonymous. They're exactly equal. 1 cubic centimeter is 1 milliliter. Right? So if you were headed for a career in the medical profession, in the past, typically, small measurements of volume were made in cc's, or cubic centimeters, right? cc, cubic centimeters. And the reason for that is that it's difficult to print cm to the 3rd power on bags and medical devices. It's easier to print cc. So these are all equal. That's equal to that is equal to that. Nowadays, most of what you'll see is milliliters. Small m, large L, right? A liter is abbreviated with a large L. So a milli, which is a small m, is ml. If you write this like that, it's wrong. That's not a milliliter. It's just ml. Or if you write this, what is that? That's a megaliter. That's a million liters. That's not a milliliter. Right? So it's important that you know what these units of measure are, their abbreviations, and actually, that's wrong. ml is wrong. It should be m capital L. And that will require some editing. Let's see, where is it? Here we go. I'm just making notes in my hard copy so that I can get that right. See, I'm wrong there. Milliliter is M capital L. Okay. Let's see. Here we go. So a liter is slightly more than a quart. Okay. These are equivalents. Now, when you look at nature, that volume right there on your slide, represented on your slide, is a volume, period. What we assign to that volume as a measurement of that volume may be different. So it could be 946 milliliters, or it could be 1 quart. It's still the same volume. Nature doesn't care. We just devise these measurements to help us with our science. But as far as nature's concerned, it could care less. 1 quart is equal to 946 milliliters. Right? Or if you go to the grocery store and you buy a gallon of milk, right? Look on it. Most measurements in the grocery store now are in both units, English system and metric system. So if you look at that gallon of milk, it'll be 1 gallon, but it'll also say 3.8 liters. Okay? I always look at stuff in the grocery store. Measurements, ingredients. I'll read the label for ingredients. Okay. Here's another important point that I want to make. When you write a number that has a decimal in it, if there's no non-zero number to the left of that decimal, you better put a 0. If you write this like this, that is wrong. This is what's known as an orphaned decimal. All decimals must be surrounded by a number. And if it's not a non-zero number, then there better be a 0 there as a placeholder. Okay? If I see that on any report, so when you do your labs, if I see that, an orphan decimal, that answer is wrong. Okay. So this is a kilogram. So here's the relationship between a kilogram and pound on Earth. On Earth, remember, because a kilogram is mass and a pound is weight, but we often associate the two. So in order to make this equivalence valid, you must be on the surface of the Earth. 1 kilogram then would apply a force of 2.2046 pounds on Earth. All right. Now, I want to make another point here. We're starting to see equivalences. This number and unit is equal to this number and unit. Whenever you see an equivalence like that, you have access to a conversion factor. In other words, you can go from any number of kilograms to any number of pounds by using this relationship. And let me see. Right, we're going to talk about that in just a minute, called unit conversion. All right, so let's move along. As an example, what's a metric ton? A metric ton is actually 1,000 kilograms. Right, so here we go. 1,000 kilograms is 1 metric ton. Now, what's a ton in the English system? Well, it's 2,000 pounds is a ton in the English system. So you have to know what you're saying. Just like, what's an ounce? Well, an ounce is a 1/16 of a pound, right? That's one type of ounce. There are several types of ounces. There's a troy ounce that's used in precious metals. That's different than that. So just illustrates the point that the English system is really messed up. Okay, so here we are with conversion factors. If you want to convert from one unit to the next, you need an equivalence. You need to demonstrate an equivalence between one unit of measure and the other. So if we say, well, 1 kilogram is equal to 2.2 pounds. I rounded it off to 1 decimal place. Notice what we can do with this equivalence, right? Mathematically speaking, if I divide both sides through by 2.2 pounds, right? That's valid. Anytime you have an equivalence, if you divide both sides through by the same number, then you still have the same relationship, an equivalence. But notice that divided into that is equal to what? 1. Or if I divide through 1 kilogram by 1 kilogram and divide this one through by 1 kilogram.
You in class?
I'm recording.
Oh, okay.
Potatoes are ready.
Oh, good.
If instead of dividing by a pound, we divide by a kilogram, then look, this becomes 1, and this becomes. Okay? So this is equal to 1, and that's equal, and this is equal to 1. See there? So if we have a number, say, I don't know, 10 kilograms, and we want to convert that to pounds, then we can multiply by 1, right? That's valid. But that doesn't get us what we want. It still gives us 10 kilograms. But we can substitute in there one of these because they're equal to 1, correct? So 10 kilograms, and here we're going to substitute like that. That's equal to 1. But notice, this unit is in the numerator, right? Anytime you see a number and its unit sitting by itself as whole number and unit, that is automatically numerator. So this is the denominator, this is the numerator, that cancels, okay? So 10 times that equals 22 pounds. 10 kilograms equals 22 pounds. I have just shown you dimensional analysis. That's the fancy name for it. Unit conversion. And the reason unit conversion works is because the conversion factor, this right here, is always equal to 1. And it's derived from an equivalence. If that equals that, then you automatically have a conversion factor at your disposal. All right. All you need to know is what's the equivalence, then you have the conversion factor. All right. So let's take a practical example, say density. Here we go. So what is density? Density is mass per unit volume. So if you have a certain volume of a substance, define volume, and measure its mass, then it's so much mass per that volume. Okay? So we write that as a formula like this. Density equals mass per unit volume. Right? That's how much mass it is if you have that much volume. Okay? So you're going to have 2 units of measure. You're going to have a mass unit and you're going to have a volume unit. All right? Your authors, I tried to use the author's representation for density. This is what I'm familiar with. They use R for density. So R equals mass divided by volume. Right? So if the volume is, standard is length, then the volume would be cubic length. Right? So if you measure the volume in terms of centimeters, then it would be cubic centimeters, right? Height, width, depth gives you a volume. So here we have the possibilities. Grams per cubic centimeter is a typical unit of measurement for density. Another one is kilograms per cubic meter is possible. Another one, and this is typically the density unit for solids. whereas gases and liquids, we generally have grams per excuse me. There we go. Grams per milliliter, because a cubic centimeter and a milliliter are equivalent. So the number won't change, but we use different units. A solid chunk of earth is typically 5.5 grams per cubic centimeter. Now, you'd have to go pretty deep, because if you just took a soil sample, the soil would be about 3.2 to 3.5 grams per cubic centimeter, because you got voids in there, air spaces and things. But that's just an example. Or if you had solid aluminum, piece of aluminum, it would be 2.7 grams per cubic centimeter. Iron would be 7.8. So for the same volume, iron weighs more, right? And gold even more than that. Okay, liquid densities, right? I just mentioned that. Pure water is 1 gram per cubic centimeter. Actually, it should be 1 gram per milliliter, but the number is the same. Seawater is a little heavier. It's a little more dense because it has lots of dissolved salts. When you give the doctor a urine sample, one of the measurements they perform on your urine is a measurement of density, right? And it's typically for a healthy person is between 1.015 and 1.030 grams per cubic centimeter, grams per milliliter. There used to be, when I was growing up, batteries in our cars had a tendency to, over time, lose the water, lose volume inside the battery. And one way to test it, test the condition of your battery, was to draw out some of that liquid into a device, and it would give you the density of the fluid inside the battery. If it was in a certain range, your battery was well charged, and if it was outside that range, it was either low charge or dead. Nowadays, we have sealed batteries, and that's not so much a problem anymore. But we use a hydrometer to measure densities of liquids. And it's simply you have a cylinder, and you have your liquid in here, and you have a weighted bottom here. It usually has a little lead in the bottom. And there are markings here. And you put that hydrometer in your liquid, and where it settles down, you read right here at the level of the liquid the density of your liquid. Okay? And it's based upon Archimedes' principle. But we're not ready to talk about that yet. Oh, I forgot I had a picture of one. So there you go. There's your lead in the bottom, and there's the measuring scale inside. Now, you can combine units of measure and the numbers that go with them. We did it for density already. We combined grams and cubic centimeters, and grams and milliliters. But it doesn't stop there. If you multiply or divide, or you combine numbers in certain ways, then you also have to keep track of the units of measure in those combinations. For instance, this first one here, the Newton. One of the formulas, and we'll discuss this when we get to Newton's second law of motion, is expressed as force equals mass times acceleration, right? So what's mass? Mass is kilograms, right? Okay. Acceleration is what? Well, you don't know this yet because I haven't told you. But acceleration is meters per second per second. In other words, how fast is your velocity changing? So if you're going meters per second fast, but that's changing every second, then you have meters per second per squared times kilograms, and that is unit of measure for force. But by the international standard also says that that is equal to a Newton of force. Okay, in honor of Isaac Newton, of course. You can have other derivations, and we're not going to go into those right now. Those are examples. But when you multiply these two numbers together, you also have to multiply the units, right? And that's why you have this unit combined, because that one was kilograms and that was meters per second squared. So there you go. So when you're doing these calculations, you have to keep track of not just the numbers, but the units also. Here's a discussion of the conversion factor, and I already did it, right? I told you what a conversion factor was, why it works, and how to use it, right? So we're not going to go through that again. This is an example of conversion. 2.54 centimeters is 1 inch, which means you can use that conversion factor or you can use this conversion factor. Doesn't matter. So if you've got an equivalence and you write it in terms of inch over centimeters, that's equivalent to centimeters over inch because they're both equal to 1, right? So they're equal to each other. You just use the one that cancels the units that you don't want and leaves you with the unit that you do want. All right, so these are the steps. I'm not going to go through these because I already did as in an example, but they're here for you to review. The one point that I didn't make was when you get an answer to a problem, and this is true for conversions as well as any other calculation, does it make sense? Does your answer make sense? Use a little intuition, and this takes practice. But if you do a calculation and the calculation says the answer should be how far is it from Earth to the moon, and your answer says 24 meters, right? Does that make sense? The moon is 24 meters away, right? The other end of my house. That doesn't make sense, right? So you say, if that doesn't make sense, I must have made an error in calculation somewhere. So you go back and check your answer, right? Does the answer make sense? Sometimes you just do an estimate. You go through the calculation in your head and you say, that's almost this, that's about that, and that's about that. Multiply, divide, and with practice, you get good at it. And you say, okay, it ought to be in the neighborhood of such and such a number. If it's not even close to that estimate, then go back and check your calculations. All right, here's another example, kilometers per hour to miles per hour. We're not going to go through that one because it's right there on the slide and you can do it yourself. Okay. All right, let's see. Sometimes The conversions that we've done so far use one conversion factor, and that's great. If you have an equivalence for the conversion that you want with one conversion factor, more power to you. Sometimes, though, one conversion factor is not enough to get you where you want to go. Right? So here we want to go from inches to meters. Right? Do you know the conversion from inches to meters? I don't. But I do know the conversion of inches to centimeters. Right? So inches cancel, leaving with centimeters. Then another conversion factor will convert from centimeters to meters. Centimeters cancel. Right? There we go. Centimeters cancel, and there's your meters. So this is what's known as the chained conversion. And since you're multiplying this number by 1 and multiply it again by 1, it's valid. As long as this number is equal to 1, you're good to go. All right. Let's see. 1st and 10. Oh, we're talking about football. 1st and 10. You got 10 yards to go. So there's your 10 yards. How many meters is that? Well, 0.914 meters is 1 yard. Right? If you know that, then the conversion says that 9.14 meters is 1st and 9.14 meters to go. Imagine what would happen to the crowd if the announcer said that. They'd all go, huh? And I'm just reiterating this one. As the unit of measure gets smaller, the number in front of it gets bigger. So the unit of measure here, the yard, is smaller than the meter. Right? So the unit of measure is getting bigger, going from yard to meters. So the number has to get smaller. So here we have altitude 4,843 meters high. How high is that in feet? Right? So we say, all right, what's the relationship? Well, 1 meter is 3.28 feet. So there you go. Cancel the meters. It leaves you with feet. So at that point, we're 15,885 feet above sea level. All right. Now, let's back to a discussion of error. Every measurement has error. So I'm going to give you a way to express that error. But first, we have to look at a number, any number, and describe it in terms of error. Let's see. Okay. So let's say we have, for example, 1.67. Let's use this one down here. 1.67. Okay. We're not going to talk about units right now. We're just talking about numbers. So it could be any units. It doesn't matter. For this number, if another scientist sees that number as your measurement, they automatically assume these digits are certain. That is, there's no error in those values. The last digit to the right is uncertain. It's essentially an educated guess. So what does that mean? Well, let's say we have a meter stick, and the measurement is, well, actually, we need 2 meters, don't we? say this is meters. So we have a meter stick here, and we have a meter stick here. So we got a distance from here to about there. And say this meter stick is marked off in tenths of a meter, right? So this is 0.6, and this is 0.7. And the measurement is right here, from there to there. So that's 1 meter here, and this is 0.6. It's between 0.6 and 0.7. So we're going to guess that it's at 0.07 between those two numbers. So it's 0.67. Okay? There's no mark there for the 0.07. It's a guess. Right? If there's a mark there, then you put that there, and then you make a guess for the next one. So the last one is uncertain. Everything before that is certain. Now, what does that have to do with significant figures? Well, significant figures are all the certain plus the one uncertain. That's the number of significant figures in that value. In this case, we have 3 significant figures. Okay? This is important because when you use your calculator, the calculator doesn't know significant figures. It gives you as many decimals as you ask for. So if you have your calculator set up to give you 1, 2, 3, 4, 5, 6, 7 decimals, it's going to give them to you. It doesn't know how many significant figures you're supposed to get in your answer. It just gives you everything. So if we say 6.8 divided by 1.67 is this value, how many of those values, 4.0718563, are you allowed to keep? Right? Because you can't keep all of them, not legally in scientific terms. All of those numbers are not significant. It's based upon the numbers that you started with. And we need some rules, right? So here are the rules for significant figures. Rule number 1, all non-zero digits are significant in the calculation, right? So if we go back, there are 2 significant figures here, and there are 3 there. Doesn't say anything about the answer yet. We need to talk about the numbers that go into the calculation. So that's what we're doing now. All right. Okay, so non-zero numbers are significant. For this number with 1, 2, 3, and 1, 2, 3, both of them have 3 significant figures. Just keep that in the back of your mind. Next, numbers that have zeros in them. There are 3 types of zeros in a number. If they're captive zeros, that is, they have a non-zero number on either side, that 0 in the middle is significant. Why? Because it holds a place. If you don't have that 0 in there, you don't have 407. You don't have 407. You would have 47. Okay? So that 0 is significant because it's captive. Both of these zeros are significant because they're both between 2 non-zero numbers. So this one has 4 significant figures. Okay, what other types of zeros are there? Well, there are zeros to the left, leading zeros. Leading zeros are always not significant. Right? As long as there's no non-zero number to the left of any of these zeros, if they're just zeros out there, then those are not significant. So this number only has 2 significant figures, right? These are just placeholders. They're important, but they're not significant. And then you have zeros to the right of non-zero numbers. Okay? Those zeros are only significant if there's a decimal point. Right? So 45.0 means there are 3 significant figures in this number. Right? That has 3 significant figures. What if we wrote it like this? That only has 2 significant figures. Right? Or if we wrote it like this. That's a different number, but it still only has 2 significant figures. Because there's no decimal point. There's no explicit decimal point in that number. There's an understood decimal right here, right? Because that's ones position, tens, hundreds, thousands. Now, how would we make 4 significant figures out of that number? If you put a decimal there, that makes these 2 significant. Okay? It's still the same number, but now instead of 2 significant figures, there are 4 because it has an explicit decimal. All right, now that we know how to define significant figures, oh, there's one more, excuse me, exact numbers. Exact numbers are either counting numbers, like have 5 people or 6 pencils. Those are exact numbers. And those exact numbers have infinite significant figures. In other words, if they're in a calculation, you can ignore them. You're only limited by the other numbers in the calculation. This is also true for conversion factors. So if I say the conversion factor 1 inch per 2.54 centimeters, that number, both the 1 inch and the 2.54 centimeters, have infinite significant figures. That's a conversion factor. It's automatically an exact number for our purposes of calculation. Now, if we get a number from our calculator that's big, like that earlier one, like this one, how do you limit the number of significant figures? Well, you need to round the number, right? So we need rules for that too. So before I get into the multiply, divide, and add, subtract rules, rounding, how do we round? Well, there are a number of ways of rounding, but we're going to use the 5 rule. If it's less than 5 to the right of the significant figure number, then you round down. And if it's greater than or equal to 5, you round up. Okay. So how would we do that with 4.0718563? If we wanted to round to 5 significant figures, start from the left, 1, 2, 3, 4, 5. That's the last position that we legally can keep. That means you look to the right, just here, ignore those. They don't count now. 5, that means we round up on this one, and we get 4.0719. Now, don't make the mistake of rounding 5 from 6 or rounding 6 from 3 and rounding round until you get to the one you want. You go to the one that you want and then look immediately to its right. That's where you apply the rule. Okay? Now, what are the rules for calculation? There's only 2. if the numbers are multiplied or divided, all you have to do is look at the numbers that are multiplied or divided, how many significant figures are in each one of those factors. Take the smallest number. That's the limit on your answer. For example, 6.8 divided by 1.67 is 4.0718563. You have 3 significant figures here, 2 there. Your answer can only have 2 significant figures. So you have to round to 2 significant figures. So we go 4, 0, right? To the right of 0 is 7. That means you round 0 up. So now you get 4.1, 2 significant figures. Everything else goes into the ether. It's gone. Add, subtract rules. Add, subtract are a little more difficult. When you add and subtract 2 numbers together, you line up the decimal points. Here's 5.687. And we're going to add 11.11. Let's see, let me do that one again. 11. There we go. Line up the decimal and just add everything together. Okay. 7, 9, 7.61. So that's what you get from this addition. How many figures can you keep down here? Well, we know that that's 4 and that's 4, but this is an addition. So you can only keep the number of decimals based on the least accurate of the numbers you added. This one is less accurate than that one. This one only goes down to 100th. This one goes to 1,000th. So you're limited right there. So that means you have to round this one up from that one. So this one makes that one 10 added to this one there. 16.80. Right? So that had 4 significant figures. This one had 4. The answer has 4, which is entirely coincidental. Right? This number of significant figures is not based upon these. It's based upon their decimal position. Okay. Let's see. That's the rounding. Okay, we talked about that already. All right. So here's a good example. If we multiply 5 times 356, 5.0 times 356, we're limited to 2 significant figures based upon 5.0. We get 1780, and we have to round it to 2 significant figures, right? So we go to 7, find that it has to be rounded up to 8, but we don't throw this one out. That position is maintained in this 0, right? So 1800 is the correct answer. And we keep those 2 zeros as placeholders, but we don't put a decimal there. Because if we put a decimal, then we're saying that they're all significant, but they're not. So we leave the decimal out. Now we only have 2 significant figures. Okay. What if, here's another possibility. Suppose we have, let's take this as our model and let's write 5, 6, 8, 7, and 11, 11, 0. Add those together. Okay. Notice that there's no decimal place. This one has an explicit, a an understood decimal here, and that one has an understood decimal there. So we line them up on those decimals, but they're not there. So where are we limited with our answer? Well, we get 16797, but we're limited here because that 0 is not significant. There's no decimal in it. So for this one, we would say 168. Let's see. We have to round this one 800. There we go. That one presents a problem. Why? Because now we think we've only got 3 significant figures when we really need 4. So here's how you solve that problem. We need scientific notation. Let's see. Excuse me. We need to convert this in such a way that we can keep 4 significant figures. So scientific notation is a way of expressing very large and very small numbers. Either way. We introduce the powers of 10. Right? So what do we have here? Well, we have 16,800. So how many powers of 10 are there? There's 1, 2, 3, 4, 5 powers of 10 possible. But when we write the number in scientific notation, this part of the number, the coefficient, is between 1 and 10. Right? So we had to move from 1, 2, 3, 4 places here. And we stored that information in this power of 10, right? So this number is no longer 16,800, it's 1.680. But in order to make them equivalent, we need to multiply it by a factor, which stored that information, 10,000 actually. This way, we get to keep 4 significant figures in our number. This way, there's no way to express it. But this way, there is. All right. So that is the definition of scientific notation. You take very large number or very small number and store the information in that number in the coefficient combined with the power of 10. Here are examples. 247 as scientific notation is 2.47 times 10 squared. So look at how we moved the decimal place. We moved it to the left, 1, 2. Right? So as the number gets smaller for the coefficient, the power of 10 gets larger. It's a positive number. If, however, we have to move the decimal to the right, we're actually making the coefficient bigger. Right? We're going from this fractional 408 to this 4.08, between 1 and 10. So we've gone 1, 2, 3, 4, 5 places in a negative direction. So 10 to the minus 5th is the power of 10 times our coefficient, 4.08. It takes practice. But notice we can make very large numbers manageable or very small numbers manageable by using scientific notation. Okay. The distance to the sun, for instance, 93 million miles. Well, 93 times 10 to the 6th is a valid exponential number, but it's not scientific notation. Scientific notation is a special case of exponential, in which the coefficient is always between 1 and 10. Okay. These are just the rules that I just illustrated for you, so you can look at those at your leisure. All right, another example, and in the interest of time, I'm going to move on. We're coming down the wire, and this video is already too long, so I'm going to move on. These are just examples. There are plenty of examples in your homework, in the Cengage Unlimited homework, which for this class is called WebAssign. And there are lots of examples in your textbook, and there are examples in the Blackboard practice tests. Right, so you've got lots of avenues for practice. And while we're on the subject, these practice exams that you can do in Blackboard are set up so that you can run through them, and they will grade them for you, the answers. It will take the answers and tell you if they're right or wrong. And then, but I don't see those values, not for the practice tests. Then you can go back and take them again and drill them until you can answer them without hesitation. And it's important that you know why you're doing the answers. That's the whole purpose of what we're doing anyway, so that you can take unknown problems and solve them that you've never seen before. All right. Notice in this one, this number 0.0003, 0.00030, this zero, the last zero, is significant, so we have to keep it. So we move 1, 2, 3, 4 places to the right, which means negative power of 10, 10 to the minus fourth. And then we have 3.0 here as our coefficient. We keep that 0 because in this number, it is significant. All right. Problem solving, right? How do you solve problems? A logical process is better than an illogical one. And I don't want you just rote memory how to solve a problem. The reason being, if you are faced with a problem that you've never seen before, then the rote memory solution won't work. You need a method of solution. So read the problem, obviously, and think about the principle that's involved. That shouldn't be too difficult because there are problems for each chapter, and each exam is only one chapter each. And then write down the information that you're given from the problem. I always find it easier to solve a problem if I extract from the word problem values and information that's given and put it on the board in a logical fashion. Extract it from the problem. Because word problems, they're designed to confuse. That's the whole, one of the purposes of word problems is to confuse. In other words, if you don't actually understand the concepts, then the word problem will spin your head around. So extract the information from the problem and then look at the information along with what is the question. Problems always have a question, and you have to know the question. If you don't know the question, you can't get the answer, right? If you give an answer without knowing the question, that's probably going to be wrong. And then devise a procedure for answering the question based upon what you've studied in that chapter. And then proceed. Don't try to fit a square peg into a round hole. Right? Look at the problem. What's the question? What's the information given? Do I need more information? Find the information. Then solve the problem. Work the problem. Don't let the problem work you. All right. So here's an example, and then we'll be done with this chapter. The Earth goes around the sun in nearly circular orbit with a radius of 93 million miles. How many miles does the Earth travel in one revolution around the sun? So in 1 year's time, as the Earth goes around the sun, how far does it travel? Right? What are we given? Well, we're given 93 million miles, 9.3 times 10 to the 7th miles, right? That's the radius. Okay? And we want to know how many miles does the Earth travel in making one revolution. So one revolution per year, right? That's how long it takes to go one revolution, 1 year. Now that's the information that we know. What's the question? How many miles? Sometimes it helps to draw a picture, right? So if here's the sun, and here's the orbit of the Earth, it's going to go around like that, like that, like that. And we want to know that distance. So what do you know about that? You know that that's nearly a circle. And the problem tells you it's nearly circular. So we're going to assume this distance is r. And what's this distance? Well, what's the circumference of a circle? Right? It's pi times the diameter. The circumference equals pi times the diameter. And the diameter is equal to 2r. So pi times 2r equals the circumference. That's what we're looking at for, the circumference. Okay? So, what information do we need to know? We really only need this one, right? Because plug in r here, times 2 times pi, and you got the distance that you've traveled, right? So all we have to do is plug in here 9.3 times 10 to the 7th miles. Solve the problem. Now we worked the problem. We didn't try to force it. We just said, what do we know? What's the question? How do you get there? So pi times 2 times 9.3 times 10 to the 7th miles will solve the problem. And there's pi. All calculators have a pi button in them. And by the way, you're going to need a calculator for this course. And if you don't already have a calculator and understand how to work it, that's one thing you want to do very early on in this course, because I'm not going to be there to teach you how to work a calculator. Besides, I don't use the kind of calculator that most people use anyway. That's another story. So learn how to use your calculator. Learn how to do multiply, divide, add, subtract. Learn where the exponent key is. So if you can put in values like this, 9.3 times 10 to the 7th miles. How do you enter that value into your calculator? How do you set up your calculator so that it'll give you answers in scientific notation? Where's the pi key? You might have to do other calculations like where's the log key? Where's the square root key? Things like that. Find out how to use your calculator for all those possibilities. And then when you get the answer, which your calculator will say it's this, maybe, round it off. How many significant figures do you have? Well, 93 million, we're assuming here, is 9.3, right? So that's only 2 significant figures. Your answer has to be 2 significant figures. 5.8 times 10 to the 8th miles. Okay? All right. And notice that pi is an exact number. It does not limit the number of significant figures. 2 is a constant. It doesn't limit them either. The only one that limits this multiplication significant figures in your answer is 93 million miles. Okay, that's it for chapter 1. And the rest of the chapters will be presented in a similar fashion.